Okay, so we finished last hour talking about symmetric cryptography, which means that the transmitter and receiver share the same key. They have knowledge about the same key. And we talked about the one-time pad as being one example of this scheme. And then in practical scheme that's used today is what possibly is recommended is this AES. But let's move on and talk about another type of cryptography, which is called asymmetric cryptography, or sometimes called public key cryptography. It's the same thing. And the idea is that a user has a private key, let's call it SK, and a public key PK. And these are SK and PK, they are connected together, right? So they form a pair, so they have a relationship between each other, right? So it's not like this is independent of that, no, so they're connected. And sometimes this private key is also called the secret key, because this is the one that you would like to keep secret. The public key, however, is something that you can basically put up on a bulletin board somewhere, or advertise in the newspaper, or put up on a web page. It's something which is not secret at all. Okay, that's why it's called a public key. And encryption is done with the public key, which is known to everyone, and decryption is done with the private key, which is a secret known only to the users. So what does this mean? So since we do encryption with the public key, that means that everyone can do encryption, because the key is free for everyone to use. So Alice can obviously use this, but all other people can do it also. But Alice, who would like to encrypt the message, use this. So everybody who wants to communicate with Bob, use Bob's public key to encrypt the plaintext. So if we want to communicate with Bob, we use Bob's public key for the encryption. The decryption, however, uses the secret key, and only Bob knows the secret key. So only Bob can decrypt. Okay. So the idea is the following, that Alice has some plaintext, M, that would like to encrypt it, and then use Bob's public key. And then we get a ciphertext C. And Bob decrypts the ciphertext using Bob's private key. Private key or secret key, if you like. So SK. The thing is that even that Alice knows how to encrypt, she doesn't know how to decrypt, right? So even Alice, okay, Alice knows M, so that's maybe a contrived example, but just to make a point here, anybody who sees C cannot figure out M, the plaintext, without knowing the secret key of Bob. Okay. So this is quite useful. So for instance, if I would like to communicate with, say, an Amazon server on the internet, the only thing I need to know is the Amazon's public key to make my communication with the web server a secret to everyone else. Okay. So that simplifies this key distribution problem quite a lot. Right. We don't need pairs of every possible pair of communicating entities, don't need to have a specific key for them. It's enough that Amazon has a public key that it makes available to everyone, for everyone to be able to communicate with the Amazon web server with confidentiality. Questions? So I won't go through an example on how to do this. It's a little bit involved, actually. Mathematics is a little bit more complicated than this, but you can trust me that there exist these schemes. So a few things about public key cryptography here. The public key is not the secret. Okay, so that's important to remember, that anybody can encrypt messages. Also Bob, the people that Bob have never met, right? Maybe this, if Bob is the Amazon server, that server would like to communicate with new customers, not only old customers, right? So this is a big advantage. The secret key, however, is a secret, right? So which means that only Bob can decrypt the message. So key distribution is quite much easier than private key encryption, but as we will see later on, it's certainly not a piece of cake, right? So one needs to take care of that in a good way. The main drawback of public key cryptography compared to symmetric key cryptography is complexity. Okay, so it takes about 100 to 1,000 times longer, more computational resources to use public key cryptography compared to private key cryptography. Okay. So a practical solution which is used is the following, is that so what is the main problem with private key cryptography? It's the key distribution problem. Okay. So then we use public key cryptography to do key distribution, to share a secret key between the two entities, and then we switch over to private key cryptography afterwards, because that's cheaper. So that's a solution that is done. So in practice, Alice and Bob use public key crypto to share a key, sometimes known also as a session key. It's a key that is generated and used for a short while. And then Alice and Bob use this private key cryptography with the session key to communicate large volumes of data. And when they're done, they throw away the session key. Okay. So then we combine the advantages of both schemes here. Questions? Okay, so we continue. Now, as we talked about here, we talked about cryptography in the sense that we would like to protect some data. So I encrypt the data, and then I send it over a public channel where anybody can read it. But the idea is that they should be unable from the ciphertext to figure out the plain text. But there are many other things which we want to do with security. So cryptography can also provide other things which are useful to us. One thing which is quite useful is something called authenticity. And this means that we can, with cryptographic methods, get a scheme that can verify that the message comes from the claimed sender. Right? And this is quite useful. For instance, if I would like to do some online banking, the bank would like to know that I am the person I claim to be, right? That the bits they get on their interface is bits which are generated by me and not by some hacker, right? So authenticity, that is to prove the ID, the true person that generated the message, is something which is quite useful. Integrity is similar, but a little bit different. And integrity is the guarantee that the message which is sent has not been altered in transmission. Okay. So when I send again from my, when I want to communicate with my bank and I say, okay, please transfer this amount of money, 1,000 krona, to this other bank account. We don't want that to be changed to 100,000 krona to the other bank account. Or at least I don't want that, right? Okay, so one wants to protect also the bits. One would like to, with authenticity, I would like to verify from the bits that the bits have been generated by a certain person or a machine. And with the integrity, I also want to make sure that these bits have not been tampered with during transmission. So again, with this banking analogy, how do we know that the web server I have in my web browser that I'm communicating with is truly the bank server and nobody else's? How do I know that the money transfer goes to the right destination and have the right amount? So these are, well, maybe we need a question mark on this also. So how do I know this? So if I have authenticity, integrity, I can guarantee this. Now, confidentiality doesn't mean that we cannot tamper with the message. Okay. just because the message from the ciphertext, it's impossible to read the message, it's not the same to say it's impossible to tamper with it. Right? So for instance, in the one, so suppose I'm a bad person and I would like to change the message and I've given the ciphertext and I can change it. Okay? Then I happen to know that this bit is super important, that I would like to change that. How do I change this? Well, I simply replace that 0 with a 1, and when the receiver is then decoding 1, 1, 0, 1, 1 plus 1, it will decode that to 0. So I can flip bits in the plain text by modifying the ciphertext. I cannot read the bits, but I can flip them, right? So confidentiality does not mean that I'm unable to tamper with the plain text, right? These are two different things. Okay. Was I clear, right? Okay. How do we do this? So there are different ways to do this. There is a private key solution and a public key solution to this. So if we start with the private key cryptography solution, then I can create something called message authentication codes, or MACs. Okay. So this is no longer medium access control, right? It's a message authentication code. Sometimes in the literature, one writes MIC, message integrity code, which is basically better, right? If you don't want to, if you think MAC, it could ever be confused with MAC. Right? But now for the purpose of this lecture, MAC stands for Message Authentication Code. So how does that work? Well, Alice has a plain text, and she feeds that through an algorithm called a MAC, which is, has a private key, K. And then we get a tag, T, which is an algorithm working on K and M. Trudy, the intruder here, reads the plain text. Okay, so the plain text is fine to send in the open. We don't want confidentiality here necessarily. We just want to be able to make sure that these bits are not tampered with. So Trudy can read M and T, the plain text and the tag, and then modify that to M prime and T prime. And the security goal, okay, and then what happens? Bob has an algorithm called verify, which looks at M prime and T prime together with K and outputs a bit, B. Okay, so B is the verify algorithm working on K, the shared secret, M prime, the bits it received, and T prime, the tag bits it received. And if B is equal to 1, then Bob can trust that M prime is equal to M. Okay, that Trudy has not changed it. Okay, if B is equal to 0, it means that, okay, M prime and T prime look suspicious. Let's throw them away. Okay, so that means that Bob accepts the message M prime if B is equal to 1 and rejects it if M prime is equal to 0. And then one can show that for a secure code, it's practically impossible for Trudy to force a message. That is to output an M prime T prime, which is not equal to MT, such that B is equal to 1. It's possible to do this with cryptography. So the key to this, how this works, has to do with the shared key, right? Okay, so the tag depends on the shared secret key. Okay. So if B is equal to 1, then Bob knows that M comes from Alice. So a side effect of this is that if B is equal to 1, Bob can be sure that M prime is equal to M, and he can also be sure that M came from Alice because only Alice knows K. Okay. So there is a level of authenticity here also. Okay. So looking at this, does this idea look vaguely familiar with something that we did earlier in the course? And what is that? Yeah, error detection codes, right? Same thing, right? We want to detect errors in, say, so suppose that this is the payload and these are the CRC bits. So why can't we use a CRC here? Yes?
Maybe it's too simple.
Too simple to
Track and too easy to manipulate.
Yeah, exactly. It's not difficult to manipulate. We know exactly what type of errors are undetectable for CRC. So, I mean, we know that, right? Nature doesn't know this, which introduced the random errors that we would like to protect on when we do error detecting codes. But an intelligent adversary knows everything about the CRC and know how to manipulate the bits so that the CRC checks, right? Okay. So this won't work, right? So that's a very good observation. Error detection is different from integrity, and it's different in the key aspect that we are trying now to defend ourselves against malicious, intelligent hackers, right? So Trudy here is smarter than noise. That's the thing. Okay, so I won't go into the detail on how these actually works. It's just that there is a family of these. Maybe touch slightly on that a little bit later. Now, there is a public key solution also, and these are known as digital signatures. And the idea is very similar in the sense that the Alice has some plain text that she wants to transmit over the channel, and she sends these in the plane, right? So these are not protected themselves, which is fine in this case because we don't care about the confidentiality here. But she generates a signature through a signature algorithm which takes the plain text and Alice secret code here to generate sigma, which is the signature of M of the plain text M, and the signature algorithm takes as input the secret key of Alice. Okay, and then it goes over the channel, and Trudy might manipulate M into M prime and sigma into sigma prime, and then Bob has a algorithm at the receiver which verifies that M prime has not been tampered with, and it's fed with the public key of Alice. So this is Alice public key. And then we can verify this. Okay. So this is very similar to the private key solution. So signing is done with Alice private key. Verification is done with Alice public key. So which means this means that only Alice can sign. Okay, because she uses her secret key. Right? Nobody else can sign. But anyone can check. Why can't everybody check? Well, because you only need PK, which is not a secret. So this is quite a big advantage, actually, because then if I'm presented with a plain text and a signature, I don't need to know anything about Alice's private key or her secret. I only need to know her public key. So when I communicate with the Amazon server, they can sign messages from the Amazon server with their private key, and since I know Amazon's public key, I can check that this actually came from Amazon, which is quite useful. All right, authenticity is implied here, and that is because Bob knows that Alice is the sender. Because she's the only one that can sign this, under the assumption that the private key, which is not PK, it is SK, sorry for that, under the assumption that the private key actually belongs to Alice. So what Bob can say with 100% assurance is that this message have been signed with somebody who has the secret key. Right. So that is what we can say. And hopefully this secret key is the secret key that belonged to Alice, and she has not, left it laying around somewhere that somebody else had picked it up. Right. Okay. Now, so that's about public key signatures. Any questions on this? Okay, so let's go on to a very useful types of functions which are used here to make things more efficient, I would say. So a hash function, what is that? A hash function is something that takes which produces an n-bit sequence x from a message m, where m has an arbitrary length. So it's almost like a function, but not, but where the input m to the hash function has let's call it L bits, and the output x has n bits. So regardless how many bits we feed into this hash function, the output is always n bits. And typically, when this is used, the number of input bits is much, much larger than n. Okay. So maybe this is like a gigabyte of data, while this might be 256 bits or something like that. Okay. So it will be 256 bits regardless of how many bits we feed in. Okay, and the practical use of this, or one practical use of this, is that x here is a good summary of m, in the sense that if I would like to check whether let me get back to that. Okay. So this digest x, we can think of that as being a summary. That's what digest means, right? It's like a compressed version of it. So x is somehow similar to the parity bits for systematic block codes, but the difference is that it's impossible, that it's very hard to find two messages with the same hash, with the same digest. Okay, so if m and m prime is not the same, it's very, very difficult to find a pair of m and m prime such that they have the same digest. Now, does this mean, okay, so if we say that no pair m and m prime is known to have the same digest, and we say that the hash function is collision free, okay, it just means that we have not been able to find these two ones. They do exist. Okay, it's just that we haven't found them yet. So, for instance, just to make this clear, in a very, very small example, say that L is equal to 4 and N is equal to 2. Okay. What are the possible input patterns? Well, it's 0, 0, 0, 0, 0, 0, 1, blah, 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 1, 1, 1, 1, right? So we have 16 input patterns. How many output patterns do we have? 4, right? 0, 0, 0, 1, 1, 0, 1, 1. So obviously, there are a number of input patterns that produces the same output patterns. This is for sure, right? So there should be, I don't know, but maybe there is just one for this one, but for sure there is some of these that have the same input. So collisions do exist. We know that. It's mathematically has to be like that. However, surprisingly enough, it's super hard to find them. Right? And that's just because in a practical thing, this space is quite large. If we have 256 bits, the number of output patterns here is just immense, right? And the number of input patterns is even more immense, right? But anyways, it's very, very difficult to find this for practical hash functions which are used in practice today. Okay, so for all practical purposes, we can view X as something that uniquely defines M, right? So given M, I can check whether X belongs to M or not. So X and M, we can find if they are connected to each other or not. So instead of doing a signature on M here, which could be quite costly because M could be gigabytes of data, then we can sign X rather than M to provide integrity. And it's easier to sign 256 bits than to sign 2 gigabytes of data. So this will save computational complexity quite a lot. So practical hash schemes is, I don't know, have you heard of MD5? No. Sometimes when you get like software updates, they have this MD5 sum to prove that, you know, whatever operating system update we got from Microsoft actually comes from Microsoft and not from somebody else, right? Here's a typical case when you really would like, you know, the data to not be tampered with. So MD5 should no longer be trusted because well, I mean, still pretty good, but there's been some collision problems with it in the sense that we can have found some M and M primes that produce the same hash. SHA-1 stands for Secure Hash Algorithm, I think. There's a SHA-1. It should not be used. SHA-2 and SHA-3 are the more modern ones here. So again, these schemes evolved during time, and one should use the latest if one has a choice. It's typically more secure. Okay, so this hash and sign paradigm. So if Alice would like to sign her message M, she doesn't sign M per se, but she runs that through a hash function first, and then get a smaller number of bits here, and then sign these bits instead with her private key. So the signature is the signature using the private key and the hash of the plain text. Okay, and that's to save complexity. And example of a practical scheme for this is something called RSA full domain hash, like this. Questions? No? Okay, certificates. So checking a signature for authenticity uses the sender's public key, right? So here, in the verification here, we use Alice public key. Okay. So Bob can make sure if B is equal to 1, that we verify. If everything seems okay, Bob can be sure that the M prime is data which is signed by somebody having access to SK, right, the secret key to which PK, the public key, belongs to. Right? So this is known. But how does Bob know that this public key and this this public key actually belongs to Alice? How do we know that? How do we know the connection between PK and Alice? Okay, so how do we know that this is true, right? That Alice actually is the person with this public key. So here's where certificates come into play. So checking a signature for authenticity uses the sender's public key. But how does Bob know that a particular public key is the public key that Alice has and nobody else? Here's the thing. If there is another person, let's call him Charlie. certifies that the public key is actually Alice's key. If that is one. And B, Bob trusts Charlie. Bob knows Charlie and trusts him implicitly. Seems to be an honest guy, right? Then Bob can trust that PKA is actually Alice's key. All right? So Charlie here is something called a certificate authority, or CA. It's a trusted organization. You know your favorite organization. I don't know what that could be, but somebody who we have trust in somehow, who's proven to be trustworthy. Maybe it's a governmental agency. Maybe you don't trust the government. Maybe there's something else, right? Okay, somebody that you trust, right? And it has this organization has a well-known public key C and a very, very secret key SKC. Then Charlie can provide Alice with a certificate saying, I, Charlie, certifies that the public key PKA belongs to Alice. With this certificate, Alice can attach this to her message or give that to potential receivers to say, hey, Charlie here tells me that this key is actually my key, right? You trust Charlie, so therefore you should trust this. And then Alice's can send this certificate to Bob, who then can verify that the certificate has been signed by Charlie. And since Bob trusts Charlie, therefore he trusts that PKA is Alice's public key. So, in a little bit of a picture here, we have Charlie, who we trust, and Charlie issues this certificate which says that PKA belongs to Alice. This is the plain text of the certificate, and then this is signed with Charlie's secret key. Okay. Then Bob, who knows Charlie's public key, can check that these bits have not been tampered with, and then deduce that, okay, this statement is actually a statement that Charlie has made, and since I trust Charlie, Bob can say, knows now, or rather trusts, that PKA belongs to Alice. Okay, so this is the certificate, right? So was the idea reasonably clear, right? So the problem we want to solve is that Bob should be reasonably sure about that a certain number of bits is actually the public key of Alice. Okay, and the way to do that is that Alice provides a certificate where somebody that Bob actually trusts and knows claims that this is the fact, the truth. So since Bob trusts Charlie, Charlie says this, Bob trusts what Charlie says, and that solves the problem. Questions? This is a little bit complex, I know this, right? So, but if you look at it, maybe you can follow the logic a little bit. Okay, so then problem solved, right? So wait a minute here. How does Charlie knows that Alice's public key is PKA? Right. So that little thing. So the thing is that Alice actually has to go to Charlie, prove her identity, and say, okay, here's my public key. Can you please write me a certificate for this, right? It's almost like you go to like a public notary, right? And you would like to get your documents somehow certified. Okay, so Alice needs to go there with her ID or whatever, right, to do this. So that's problem number one. Problem number two is, how does Bob know that Charlie's public key is PKC? How does Bob, who trusts Charlie, but how does Bob know that there is a public key C which belongs to Charlie? Right? That's also a problem. And this is solved very clumsily, that these public keys are actually hard-coded into the operating system of computers. So whenever you install an operating system here, it comes with a bunch of public keys to these certificate organizations. And then you better trust that Apple or Microsoft or somebody else actually put in the right bits there, right? But maybe they have gone to Charlie also and say, okay, so now I know you're Charlie, I'm Apple, right? Are you sure about these bits and so forth? And then they organize this. Yes.
Would you say that's a bad solution?
Yeah, it's a bad solution because there are many of these certificate authorities. So every now and then somebody is compromised, right? And there are hundreds, if not thousands of them also. So it's a maintenance problem, I would say. So I think, I don't know this for a fact, so take this with a grain of salt, but I think some of these security updates you get is when companies say, okay, I don't trust this certificate authority anymore, right? So I remove that from my list of trusted CAs. Okay, and then these certificates then are in a particular format, and which is much more complicated than I actually explained here, because there are many different ways you can sign with different algorithms. You can sign signatures and so forth, and there are many of these CAs, which is a problem. So if we want to connect back to our protocol stack, so where do we do security? Well, there are two main ways, and maybe from a user's perspective, there is something called transport layer security, which is between the application layer and transport layer. So as soon when you log on to a website or something like that, and you see that small key lock thing, right? That means that the encryption, that data you send over the web browser, the HTTP messages, application layer messages, go through a secure transport layer. Okay, so the TLS here, the transport layer security, is, so if we have the application layer here, and here we have the transport layer, and you know transport layer should be like UDP or TCP or whatever, right? And then we have IP below here. Then we put in here the TLS here, right? So it's just above TCP and UDP. So this TLS is a modern version of this, sometimes an older thing called secure socket layer. So it can be used then to provide confidentiality, integrity, and also optionally authenticity. So it's a nice thing to have. So TLS is used by this HTTPS, S for secure. And basically you should use it, right? Whenever you have the chance, use it. There is also something called IPsec. I didn't put up a slide on that, so but I just wanted to mention that you know this VPN, virtual private networks, uses IPsec, a secure version of IP. Yeah. Now, going back to reality here, in the sense that what are security problems, and they are quite wide. So there are technical solutions to doing this, But as you know, the problem is typically humans here, that humans are doing bad things. So no security technology is secure if it's not used in a secure way, right? So there are many ways to screw up unintentionally, right? But there is also many ways to fool users into do bad things. You know, weak passwords, answering phishing emails, and so forth. I used to have a PhD student in the group who got an email saying, okay, this is IT service at Chalmers, could you please provide me, log on to this website and reset your password? And he did it, right? And when he pressed return, he said like, was this a good idea or not? And then he actually called the IT service and they say, are you an idiot or what? And they had to block all of his access, right, to Chalmers services and so forth. So these phishing emails is a severe problem. Also people calling up, claiming to be, you know, Microsoft or whatever, and fooling people to log on to malicious websites and share their credit card numbers or whatever, right? So there are many of these problems. But problems should also come from badly configured systems. Okay, so you use security in the wrong way, or bugs for that matter. This happens actually, right? That there are bugs in the security algorithm, and that we use them in the wrong way. Yeah. So it's what can I say? It's this. Communication information technology, ICT, information and communication technology is a wonderful tool, right? It can solve many problems, but it also opens us up for misuse, attacks by people who want to steal money or terrorists or warfare for that matter, right? So it's so one has to be. When designing systems, one should always take security into account, and one should do that as early as possible, and one should bring in the experts to do the work, not try to do that by oneself. It's much easier to get a system, design a system to be secure from the beginning, than take an insecure system and try to fix it in the afterwards. So with that sad note, with that I think we end for today, and that's it for new material in the course. Next time we see each other, it's going to be like, I don't know, a little bit of a review, questions and answers. So whatever questions you have on the course and the course material, bring that on Thursday and we can talk about it. All right? See ya.